And we're live. Also posting this on Discord. Nice. I think we're live. Posting this on Discord. Nice. Yeah. Okay. I think we'll have already 12 viewers. Hello, everyone. Really excited to see you here. We have me, Artemi from the Sherlock team here, and also Jeff and Teddy from Notional team. Yeah, hello everyone who is watching us in the recording. This is a code walkthrough for the Notional Leveraged Vaults update. I think a lot of OG Watsons at Sherlock knows about the Notional already. I think it's like the contest number 6 for the Notional on Sherlock. So super excited, everyone, to start this contest. The contest is already live, so you can join this contest whenever you want. And this code walkthrough will have just regular questions, regular overview about the scope. You can ask your questions in the Twitter, or you can also ask your questions in the YouTube. We'll see, and we'll have a Q&A session after the main part. So really looking forward to the questions. And yep. Hello, everyone.
All right, great. Thanks, Artemi. So I'll just start off with talking through the scope, and we'll maybe expand on some of the contest Q&A. And then from there, we'll kind of do a walkthrough of this audit scope and maybe start to deep dive into the code. So the scope is here. I'm sure all the auditors are taking a look at this. Well, like the features in scope here, one of them is this vault rewarded lib, and we'll talk about that. That is sort of like one feature that kind of sits on its own, and it's an extension of an existing strategy that we have. And then the second sort of larger component of the audit here are these staking vaults. So as you can see, there's a number of variations of these staking vaults that we're auditing here, primarily focused around Pendle. But we'll talk about that in more depth. So this is that'd be the scope. In terms of the Q&A, some of this is pretty self-explanatory, but we just wanted to kind of talk through some of these answers a little bit, just to make sure we can add a little bit more context if that's useful. This one here, okay, so this one here, surround permission functions. There's 2 permission functions within the scope of this contest. There are more permission functions outside of this in the larger Notional ecosystem, but we want to call these 2 out. So one is in the vault rewarder lib. We have a method that allows us to whitelist incentive tokens for this vault. So this is like a governance only method, and so issues around like governance setting some weird values here, we probably wouldn't consider that valid. So we expect governance to kind of be judicious in how they call this function. The second one is around this force withdraw method in the that's available across all the staking vaults. There will be a permission role, someone who like a multi-sig that's allowed to call emergency exit, and this will force an account to basically enter some sort of withdraw queue to exit the vault. So this role can't like forcibly take money from the account. It can only sort of cause them to go into like some sort of exit queue. I don't know, Teddy, if you wanted to add any additional details there.
Yeah, I don't think there's a ton more to say. I think it's really when we think about kind of like the risk of these strategies, in general, we're going to set governance parameters such that we're comfortable not being able to liquidate for the duration of time that we expect an account to be stuck in a withdrawal queue. So the ability to like emergency exit by forcing an account into whatever the withdrawal process is for the specific asset, we would expect that to basically ensure that we would be able to recoup the asset, like get the actual asset back, so be able to redeem the underlying asset in a short enough time period such that the protocol is not at risk of insolvency. So that's kind of the thinking behind the forced withdrawal.
All right, great. In terms of off-chain mechanisms here, there's liquidation bots. Those are used across all of Notional. And in the case of the Vault Rewarder Lib, we have these reinvestment bots that come and, claim tokens and reinvest them back in the strategy. We expect those to be working properly. So just want to call that out. Broken assumptions about function behavior. So this one, so I think two things I want to call out here. One is in scope is this Pendle PT Oracle. So what this Pendle PT Oracle is doing is it's reporting back the Oracle price for a Pendle PT token. We expect that we use the Pendle PT like TWAP, internal TWAP, to get part of that price. And so, there's a single source for that data, and we expect that it cannot be easily manipulated. So that is an assumption that we have, and something that we kind of have checked with the Pendle team. But if Watsons do find issues with that, that's something we would definitely consider. Something in the not in scope is the single-sided LP vault, but within those we have these read-only reentrancy checks against Balancer, V2, and Curve. And those protocols are vulnerable to this read-only reentrancy type attack with total supply manipulation. So we do not believe that anything similar can be done against any of these protocols that we're integrating with within this contest. But again, that's something we specifically want to call out, as we've seen it in the past, and we want to make sure that we're protected against it here. So any sort of read-only reentrancy manipulation, I think, would be kind of definitely in scope here. And then, okay, so acceptable issues and risks. So inside one of the libraries, there is a hard-coded trade path to exit staked Athena USDE back through SDI on a very specific curve pool. At the time of writing these contracts, that was it's a primary venue for DEX liquidity against staked USDE. So this is sort of like a special case, hard coding of a pool like this. We typically don't do that. If in the future, kind of liquidity moves or shifts for these Athena vaults, we would have to upgrade the contract and find, ensure that we are able to trade on the correct venue. So I just want to call that out. And then the second one, I think Teddy already touched on this, but in some of these leveraged restaking strategies, we rely on being able to withdraw from a protocol like EtherFi or Kelp. Those protocols will have to withdraw from EigenLayer and perhaps some sort of underlying staking token. So like Teddy mentioned, we expect to configure the system such that we expect to have enough margin. The account should have enough margin to sort of safely sit in an execute for some reasonable amount of time. So so those are sort of risks that we're aware of and are accepting. Great. So with that, I'm gonna, we have a link here to a Google Doc, which is sort of a more in-depth kind of outlining of the features that we developed and sort of some of the expectations here. So I'll just kind of talk through this at a high level, and then from there we can look at the code. So so the first feature is the Vault Rewarder Lib, and again, this feature kind of stands on its own. It's an extension of the existing single-sided LP strategy. And the background here is that the way the single-sided LP strategy works is on Notional. Currently, you would like maybe borrow ETH from Notional lenders. You deploy it into, say, a balancer wrap staked ETH liquidity pool, and then you'd go stake it on Aura. From Aura, you might receive additional rewards like BAL, additional incentive tokens like BAL and Aura. And currently, all the vaults run in what we call automatic reinvest mode. So those Aura and BAL incentives are claimed periodically by a bot. The bot sells the Aura and BAL tokens and then like re-enters the pool, giving all the account holders more LP tokens as a result. And so for the users of these vaults, they see organic yield. They see their position always increasing, sort of in terms of the token that they borrowed. But this is, what we found from operating this is that this isn't always ideal. For one, there's gas costs associated with constantly doing these reinvestments. And on mainnet, those can be significant. We also have seen that users want to keep those incentive tokens, right? Some users want to, or like to pursue these strategies because they like the BAL token, or they want exposure to the CRV token. And so, and third, we've also seen instances where protocols want to directly incentivize engagement in these vaults without having to incentivize through Aura or Convex. So the extension here with the Vault Rewarder Lib allows us to do that. There's two additional like modes that each incentive token can enter into. The first one is an account claim mode. And so there's a method on the Vault Rewarder Lib called update reward token. And what this allows governance to do is whitelist one of the reward tokens on a vault, say balancer on a wrap staked ETH vault. And we can set the emission rate to 0. So what this would cause the contract to do now is start tracking how much BAL it's claiming every time it runs a claim reward, and sort of do some internal accounting to associate how much BAL each account has a claim on. So now when an account exits or modifies their position, they will directly receive their share of this incentive token. So that's the account claim mode. There's a setting in there called force claim after. This is a setting that we can set on the vault. It's a time range where we sort of enforce that an account actually claims the tokens off of the booster protocol like Aura or Convex. The reason why we would have this timestamp or this kind of time lag setting is now on a L2 like Arbitrum, it's basically free to constantly kind of claim these rewards. On mainnet, it adds about 120K gas. So setting this, force claim time to maybe a couple days or something like that ensures that, accounts who are entering and exiting the position aren't sort of claiming dust amounts of incentive tokens and spending additional gas when they don't need to. So the second thing that this reward lib enables is an emission rate. So for the emission rate, what this setting does is what it allows us to do is say if, for example, we're doing this on Arbitrum right now. So as part of the Arbitrum, STIP program, one of our leveraged vaults is receiving additional ARB incentives directly from Lido. And so while we're doing this manually, this emission rate would allow us to basically set the emission rate of ARB for all the vault users over a specific period of time. It would transfer the ARB to the vault, and the vault would sort of calculate how much ARB each account holder is allowed to claim as they enter and exit the vault. So it works a little differently from the claim because it's not reliant on the booster protocol to receive the tokens. The contract will have all the tokens it needs to distribute, and it's just sort of calculating how much it's distributing kind of linearly over a period of time. That's that. I can stop here, and before we get into the staking vaults, and I can just kind of finish this up, we can take a little look at the code for the vault rewarder lib, since it's kind of distinct from the other feature. So here I'll just call out where it's integrated into the existing single-sided LP strategy. So whenever a vault enters, or wherever an account enters, we'll update account rewards. Whenever they exit, we'll also call the same method. And there's some kind of delegate calls out to this library here as well. So inside the Vault Rewarder lib, the sort of architecture here, the structure here is that this Vault Rewarder lib is going to be like a library. It's going to be deployed. There's going to be like one instance of this contract deployed on a given chain. And the single-sided LP vault base is going to do like delegate calls into this. So this contract is going to have access to the storage and tokens on the calling vault. Like this code is not going to be like inside of each vault individually. Just to kind of recap what we talked about, this is the update reward token. It's guarded by only allowing the notional owner to call. So here we are able to set an emission rate if we want to. There's two kind of tabs here. One is that where we're updating an existing reward token, and then the second one is where we're adding a new reward token. So governance is gonna, set the index here on the array. Going down here, I won't kind of go through this in complete detail. One thing here is like we will be able to extend this with different kind of claim types as we go here. So that's something we're anticipating. Won't go into everything in detail. So all the kind of reward accumulation calculations are done down here. This is kind of using like what should be like a pretty familiar kind of like accumulation math that you kind of see generally. So I think that kind of covers it on this rewarder lib thing. If there are any more like specific questions, happy to answer that in Discord. So go back to this here. Okay, so the kind of larger portion of this contest surrounds these base staking vaults, and similar to how we have the single-sided LP strategy. So the single-sided LP strategy is built around the concept of borrowing one token and going into like a liquidity pool where the assets are roughly pegged or trade, sort of in line with each other, like a stable pool. And the anticipation that there's some sort of like incentives given to LPs for providing liquidity. So that's kind of like the idea of that strategy, and like the leverage vaults allow users to kind of amplify the returns on that kind of activity. The base staking vault is sort of like the basis for another type of strategy where we're going to be borrowing one token and sort of exchanging it into a staking token somehow. And that staking token is, again, pegged to the value of the borrow token in some way, but it's sort of fully exposed to the staking strategy, right? So in a single-sided LP strategy, may be like partially exposed at kind of varying levels, depending on where the liquidity in the pool is sitting at that moment in time. And you're sort of exposed to different risks as a result. In these staking strategies, you're fully exposed to the staking token. You get full exposure, and as a result, you have other sort of risks that you're exposed to, primarily like getting out of the staking token. And so getting out of that staking token is really going to be kind of bespoke to each type of strategy that we pursue here. In this audit, we're looking at liquid restaking like EtherFi Kelp. We're looking at Athena. But in the future, it's also possible that, we look at things like staked Aave, staking, doing sort of participating in VE economics, right? Where the VE token is pegged to the underlying, to the borrowed asset. So so we're trying to design this strategy to be extensible into the future and relatively flexible for us. So when you look at the code, there's a lot of inheritance. There's like calling into kind of like libraries and things like that. And the idea there is to sort of set up a structure where we can continue to extend these staking strategies sort of quickly and as new opportunities arise.
Jeff, sorry, can I just say a few words on the sort of redemption illiquidity stuff? Yeah. So so this base staking vault, these staking strategies, the primary risk is the potential illiquidity and unredeemability of the asset that the vault is holding, right? So from the Notional protocol perspective, what we're doing here is we're taking the approach of listing vaults where the staking token is ultimately going to resolve to the borrow token. Like there's some established pathway for the staking token to ultimately like be one-to-one resolve back to the token that the vault is borrowing, right? And then there's some like period of time that it takes for that to happen, right? And during this period of time, or even prior to that, it might be impossible to liquidate the asset because it is, not tradable. There's not sufficient liquidity, whatever. And like part of the reason these staking vaults were doing these things is to enable us to like lever up on these assets, which are not instantly liquidatable, right? And anyway, so there's this period of time where you want to get out until you're actually able to get out. And like the way we think about it from a risk perspective for the protocol is that, we are going to set governance parameters with some estimation of how long that period of time could be, and be sure that we are comfortable holding the asset for the full period of time without producing any insolvency for the protocol. So that's like, and that manifests itself in a few ways in the code. So for example, in the liquidation function, we revert if it causes an insolvency on the account, right? Because if the account becomes insolvent due to like temporarily the price of the asset in the market is trading at some level such that if it was liquidated at that level, the account would become insolvent. We don't want that to happen because like we've set the governance parameters such that we are comfortable just holding the asset until it resolves back to the borrowed currency. So that's like the general risk approach that we're taking here. I think that's like helpful to, have as some context when you're looking at this. Yeah.
Thanks, Teddy. Yeah, Jeff, I think you're muted. And also great thing, we'll have already 200 viewers. So that's awesome. 200 security searches. And yeah, Jeff, please continue.
Are they able to see my screen right now, or? Okay,
Yes.
great, thank you. Yeah, okay, so I just wanted to share this snippet of code. This is inside the base staking vault strategy, and this is what Teddy was just mentioning. So in this deleverage account call, we're proxying it, and we're doing a couple checks here. We're checking that they're not insolvent, and we're also checking that as a result of liquidation, their collateral ratio is increasing, right? So it's not enough to check that they're insolvent. It may be that the liquidation puts them into insolvency. So very great. Go back to the other screen here. Okay, great. So that was so just to kind of walk through the basically the stages, the life cycle of the vaults that you're looking at with this base staking vault here. I'll talk through a little bit here, and then I have a diagram. And so these vaults exist in the context of the broader Notional V3 system. So the way this works is that we will deploy a base staking. We'll deploy a staking vault with specific strategy, and then what we'll do is we will we'll whitelist it into Notional. So there's going to be a specific vault address, and from there, Notional is going to handle the borrowing, the depositing, the collateral checks, like the liquidation logic. So all of that code exists in the kind of main Notional V3 contract. All the vault is responsible for is these kind of 4 actions here. So when Notional gives the vault funds, it's going to call this method deposit from Notional. And each one of these staking vaults is going to have some kind of implementation of how it gets those borrowed funds into its kind of like staking token. When it's done with that, it's going to tell Notional how many staking tokens it generated as a result, and Notional is going to record that and then do a check. So it's going to do a check that the value of those of this account's position is sufficiently collateralized. And the way it's going to do that is it's going to ask the vault, basically on demand, like, hey, what's the value of this particular account's position? So, and similarly, the vault is responsible for unwinding that position. So, in general, like when the account exits, the strategy will basically go through, all right, thanks, Teddy. Basically go through one of 2 possible paths. One is that in general, what we would expect is that there's some sort of on-chain liquidity for the staking token, and the staking token will be sold and the account can sort of exit more or less instantaneously. If we are in the second path where the account is in this kind of withdraw request mode where they're temporarily illiquid, the exit, like they won't be able to exit until like that request has been sort of finalized, and they can actually retrieve the borrowed tokens from the staking protocol. And we just kind of looked at the code a little bit for this during liquidations. We do these valuation checks to kind of ensure that we don't sort of liquidate into insolvency as a result of a temporary like kind of price dislocation. And secondly, these withdrawal requests can be non-fungible, right? So in Ether5, for example, you kind of quite literally get a non-fungible token to mark your place in the withdrawal queue. So within these staking vaults, we have some internal accounting to sort of like break up these withdrawal requests to ensure that during a liquidation, we can sort of kind of fungibly break up, like kind of split up a withdrawal request to ensure that the liquidator gets one portion and the account receives, their portion. So we have this kind of like withdrawal request library. So this one, we can this logic, this accounting logic is kind of in this withdrawal request base contract, and it's like, as we'll take a look at it, there's some sort of internal accounting logic that we have, and then there's a lot of like implementation specific logic where we'll have to kind of like maneuver around how each external protocol has implemented their kind of like withdrawal request methodology. So and the last thing we'll call out here is the Pendle PT vaults. So the vaults, the actual implementations that we're probably going to go live with after this audit are going to be allowing exposure to Pendle PT tokens. And so each Pendle PT token will have a very like kind of defined expiration date. And so we'll be matching one vault to one PT token, one PT expiration date. This sort of just kind of outlines kind of what's going to happen here. More or less, we're going to be selling the PT tokens on the markets when you exit, and selling again. So it's going to be two sort of DEX executions on the way out, and then after expiration, we'll be withdrawing manually. So with that, I'm going to do kind of like, okay, so this diagram is a little bit intimidating, but not all parts of it are sort of fully relevant. But this is going to just kind of recap visually what we discussed a little bit with kind of what the role of the vault is. So on Notional V3, there's a contract called Vault Account Action. It exposes three methods that account holders can call. So it's enter position, enter vault, roll your vault position, and exit vault. So we discussed enter and exit. Roll vault position is mostly for managing your fixed rate maturity. So in Notional, unlike other protocols, we allow borrowing at variable rates and potentially multiple fixed rate maturities. So roll position just allows the account holder to kind of like switch their maturity, switch their borrow type. Again, the leverage vault is what we're auditing here. And so this is the code we're looking at. And we have the deposit, redeem, so enter and exit. And then we have this convert strategy to underlying, which is going to get your valuation.
Jeff,
yes.
Quick note here. So in the chat, guys asking to zoom in the graph, please.
Sure.
In some cases.
Let's zoom. Let's zoom a little bit more.
Yeah, nice.
Okay,
Yes.
We can do it a little bit more here. Okay, so like I said, enter here goes through deposit from Notional, exit goes to redeem. And so those are the main things that, where most of the action is going to occur. And this convert strategy underlying, that's getting your sort of valuation for a given position. There's this method which is not like really doing anything in these vaults. So this is kind of like esoteric, and you can kind of read the description here, but this is like not going to be called or used within the context of these vaults. And the last thing that I wanted to point out here, which is like not totally obvious is that on all the contracts you see here in the vault rewarder lib and in the base staking vault, you'll see a method called deleverage account. And what's happening here is that there's a setting within Notional which enforces that the vault must be called in order to initiate a liquidation. And what this allows us to do is implement some custom logic for a given strategy during liquidation. So, like I mentioned before, for these balancer and curve kind of like single-sided LP vaults, we have to check if we're within some sort of read-only kind of reentrancy state and revert. For these staking vaults, like we just showed, we have to check if we're potentially going to enter into an insolvency before we liquidate. So you'll see those methods. They kind of like have a call into Notional V3 to execute the deleveraging. Within this function on the Notional V3 side, it's going to calculate sort of like how much of the position needs to be liquidated and things like that. So that's kind of like, this chart is in the this graphic is in the doc in this doc, and I think that's kind of like those are kind of like the relevant bits. All right, with that we can look at some code. So here. Here, we'll start with the base staking vault. So just kind of review the bits that we discussed. So the base staking vault is defined sort of by the staking token, right? So in case of an EtherFi vault, this is going to be wrapped EtherFi token. In case of a Pendle, like a Pendle PT vault, this is going to be the PT token, right? The borrow token is the token you're borrowing from Notional in order to enter into this position. And then the redemption token, now this may vary a little bit, right? So like in a Pendle PT vault, the redemption token is potentially like ETH, right? Not like so the Pendle PT vault may spit out EtherFi ETH as a result of exiting, but like when you go through an underlying withdrawal request, it's ETH. So there are cases where these things are like the borrow token, the redemption token are like not always the same, and so we do distinguish them here. Again, it's possible that we borrow like a liquid staking token like wrap staked ETH to go into like a staking strategy, but coming out it's going to be ETH or something like that. The evaluation function is here. One thing we point out, so withdrawal requests may have some different valuation. So we do call into like this kind of abstract function, this virtual function here, where there might be some kind of different implementation. But in general, we have like this trading module, which has like a registry of different oracles, and the valuation is generally just going to be whatever kind of market price for the staking token we see from oracles at that point in time. So there's a virtual function here to stake your tokens. Deposit from Notional here is pretty straightforward. We're going to receive however we're going to know how much the borrow token we're getting at this point in time. We check that they don't have any sort of withdrawal requests open, and then we go ahead and stake the tokens. Generally, this part of these strategies is like pretty straightforward. Nothing like crazy fancy here. Redemptions is where like things can get a little tricky. So when we have a withdrawal request, the withdrawal requests are always like exiting the account's position in full. So anytime there's a withdrawal request, you're locked out from depositing, and therefore you kind of just have to wait out the this withdrawal period before you can exit the position. So if there's a active withdrawal request, you're always falling into the else block. we're gonna like finalize it. So we're gonna call the protocol to get the funds back, and then it may be that, you know, in this case, we need to execute some sort of trade. So example here may be that like perhaps in Kelp DAO, you receive wrap staked ETH as a result of the withdrawal request. You borrowed ETH, so we're gonna have to do some sort of trade to get you back to ETH before we close out your position. In the instant redemption scenario, there's going to be a DEX that you trade your staking token out through it directly. So this should be like relatively straightforward. I'll just on these trades here, you'll see these like execute trade methods in here. So what this does is it calls through this trading module library that we have. So the trading module has a number of checks in it where it like supports a number of DEXs and it checks how much we're going in, how much tokens are coming in, how many tokens are coming out. It sets the approvals and kind of does a lot of that kind of trading logic. And each trading pair and DEX, so for example, wrap staked ETH to ETH on Curve, that combination needs to be explicitly whitelisted for an address. So like users so when we deploy one of these vaults, we'll go ahead and like explicitly whitelist which like particular pools and which tokens can be traded by the vault. The trading module will like enforce those permissions, and therefore like users like when they kind of input these like trading parameters or something, they're kind of like locked into going down like a certain path. So I just want to call that out. And then we kind of discussed this deleveraging method here around checking the insolvencies, and then this split withdrawal request. We kind of discussed that as well. And last thing here, so these are kind of three methods that sit on these staking vaults kind of in general. One is the initiate withdraw. So what this does is it allows an account to go initiate, voluntarily initiate, put themselves into a withdrawal queue. So we don't allow them to do this if they are in liquidation territory. Like that would be a way for them to maybe put themselves in the queue to avoid like a liquidation or something like that. So in the case that they do need to be forcibly put into the queue, we have that emergency exit rule that can kind of like forcibly put the account into the queue. So that's what we discussed earlier. And this method down here, this is non-authenticated, and what all this does here is there are scenarios where this like your withdraw queue is available to kind of be completed and you can pull your funds out. But we don't want the account to sort of go idle and not actually pull the funds off of the external protocol. So for example, in EtherFi, when you're able to pull your ETH off, it's still exposed to the broader like slashing risk of the entire protocol. So the best thing to do is just get your funds off of the protocol back onto the vault, where it's sort of like where the value is sort of like crystallized. So this allows anyone to call that method. It won't actually remove the funds from the account or do anything like that. It just sort of like kind of gets the funds off the external protocol back onto the vault. So the withdrawal request base, so this is inherited here. You can take a look at it. In this file, again, this is like a lot of accounting logic and math, so definitely, kind of look at it carefully. But I won't kind of go into too much detail. There are a number of like sort of virtual methods up here, which are sort of like implementation specific for the different for the different protocols that we will interact with. So I'll take a look at the Athena one because it's a little bit unique. So you can see this is an actual implementation contract. This one's not abstract and will get deployed. Generally, these are pretty straightforward. They're just calling into these libraries. So if we look at the Athena library, there's a couple things to note. So when we initiate a withdraw, the way Athena handles these withdraws so the withdrawal would be from if you have staked SUSDE, you want to unwind it to go back to USDE. When you do that withdraw, there's a cooldown that's there's like a cooldown timestamp that's set once per address. So we don't want to lock out the entire vault from initiating additional cooldowns. So what we're going to do here is we're going to transfer the portion of SUSDE that this particular account has to like this kind of holder contract. So this holder contract is defined here. It's going to be sort of like this minimal proxy that is just going to hold the SUSDE, initiate a cooldown fully on that address, and sort of wait it out. So the result of this is that you're going to get an address for this new proxy contract that's holding the account's SUSDE and waiting out the cooldown, and that's going to be the request ID, right? And then when we come back through here, we're going to go call that holder and get, when it's able to kind of fully cool down. When the cooldown is completed, it's going to transfer back the USDE back to the vault. So so that's an example of some sort of specific implementation for staking strategy. We have other ones here for EtherFi. Here we're handling the NFT that we receive and checking whether or not we can draw it. For Kelp, there's different method signatures here, and then furthermore, at the time of writing this code, Kelp just supported receiving STETH. So we also have to withdraw from Lido if we're kind of fully going through this process, and so on and so forth. So so that's that, and then we can take a look at the Pendle contract as well. So again, Pendle has some of its own kind of special dynamics here. When we're staking tokens, we're going to the Pendle market and we're swapping for PT. I'll note here. So when we swap into PT tokens, we are dependent on these approx params, and these are kind of best accessible from a Pendle, the Pendle off-chain API. So they're going to sort of calculate how much PT you can receive for the input tokens. So in the odd case that that API is unavailable or something like that, the limitation here is that you wouldn't be able to enter the vault, which we kind of think is an acceptable risk. I guess I didn't put in this Q&A. I guess we could. But you should always be able to exit the vault. When you exit the vault, you swap exact PT for SY, and this does not require an off-chain calculation. You can always sell your PT for the exit token, even if the Pendle API is somehow down, right? So that API is off-chain. So just call that out. Maybe put that in the Q&A. Arvin. Again, and then with the Pendle stuff, It's functionally very similar to the staking vaults. It's just namely like when you're kind of like exiting this position, you're first redeeming your Pendle tokens, and then you're kind of like then from there you're kind of doing the kind of withdraw queue stuff. So so if you look at one of these implementations like the Pendle PT EtherFi, it's it first is going to a little lost here. So EtherFi. It's gonna go through. Well, probably have to find the exact implementation here, but it's gonna first initiate the SY like redemption of the PT, and then it's gonna kind of go through the EtherFi specific withdraw implementation. I saw some questions, but I don't know where to. Oh, here.
Yeah. So let's move on to the Q&A session. So guys,
Yeah, sure.
I think we have 274 viewers on the stream, so really excited about that. Thanks again, Jeff, for the comprehensive code walkthrough. So really appreciate this. So guys, yeah, if you have any questions to Jeff or to Notional team, you can ask it here. You can ask it in the Twitter. You can ask it in the YouTube. We'll see all the questions in the chat. And also, of course, for example, for the guys who is watching us in the recording, you can ask all the questions in the Discord, in the Sherlock's Discord as well.
Okay, so I see one question here from Tricomas. Here we'll just kind of share the screen here. So for Vault Rewarder Lib here, so generally speaking, as much as we can across the code base, where things are like strictly required, we're going to put them in the code. So you can kind of like look at those required statements and kind of like judge whether or not they can be met. For this one here, again, one is like it's coming from governance. Two is that since we're going into like this account claim mode, we're checking that the trading module is not allowed to sell the tokens from this vault. So this may be that like we have a vault that receives BAL incentives. We want to move to the point where the accounts receive the BAL incentives. We're going to go turn off the vault's ability to sell BAL tokens like altogether. And we're going to check that here, right? Now, you can argue that like, oh, you might turn on afterwards or whatever, but like, we're not going to do that. And it's not really a way to like actively check this. And then going down here, so the way this is structured is there's an array of whitelisted reward tokens. So the governance contract is going to come in and like say, I'm going to update the 0 index. I'm going to update the 1 index or whatever. Now, if the 1 index is the length, then it's going to create it's going to push into that array. So doing some checks here, and we're double checking that we're not like changing the reward token or something like that, right? So again, if this were open to anyone, weird stuff could happen, but this is like the governance. This is the governance function. So generally we're just checking that we didn't make any weird mistakes when calling this function. For the force withdraw, there are no on-chain checks here. It's a lot broader in terms of like the restriction here. It's only that this particular role is enabled, so that the account only has this role. I think with this, it's the emergency exit role, and there's all kinds of weird ways that we could want to put someone into this withdraw queue. There's all kinds of sort of unknown variables that can occur from like some sort of depegging event, some sort of kind of smart contract issue upstream, and a lot of these things are not like really possible to be validated on chain. So but we deem it necessary as a consequence of these vaults. And I think the main thing to check here is that initiating a forced withdrawal does not result in a loss of funds for the account, right? They may stop earning yield, but they're sort of going to be frozen in time and kind of like pushed out of the vault, sort of in a graceful manner. Yeah. So the sequencer stuff. This is in the context. This is in the Q&A context. We do check the Chainlink Oracle for the sequencer uptime, and so if the Oracle, so inside the Oracle, it checks that. We can take a look here. There's some sort of sequencer check here. If we revert here, it will revert any sort of entry into the position or any sort of exit out of the position or any sort of liquidation, because in all of those methods, we're going to go get the valuation. The valuation call will fail, and kind of the whole transaction is going to fail.
Okay. Yeah, I think we don't have any questions for now, so we can finish at this moment. If anyone will have any questions, you can ask them in the Discord. So yeah, thanks everyone for joining us today. Good luck with the contest. It's already started, so you can join it on the Sherlock.xyz and everyone contest. And thanks, Jeff. Thanks a lot. Thanks also to the Daddy for this code walkthrough. And yeah, thank you, everyone.
All right, cheers. Thanks, Artemy, for doing.
Yeah.